Hi there, this is Zachary Lythgoe, and this is a project on microgrid disturbance classification using a Phasor measurement unit, or a PMU, and an Arduino. So the problem we're trying to solve here is, can we predict or classify different disturbances to microgrid using this hardware, using machine learning? So the reason you would want to classify these in the first place is that microgrids themselves are much less stable than a larger grid, mostly due to the fact that they have less generation to work with. So if a large load were to kick on, all of a sudden that would consume a larger proportion of the available generation your microgrid has. So, and if you were to pair that with, say, with renewable energy, and say the wind dies down and the solar panels are covered by clouds right as you try to turn on some large loads, you can see larger stability issues with the microgrid, which are important to avoid. So here we have just to generate data. We don't have a real grid to work with, so this is all simulated using Simulink done by a professor at ASU. Here we have just one disruption is a 10 horsepower and 20 horsepower motor turning on at the same time, which we call class 6. You can see this happens at 0.1 seconds. You can see during that time that the current increases significantly in magnitude, and there's also some distortion here about half a cycle later. So in order to simulate this, we're using a USB 6351, which has two analog outputs that are able to output at the same sample rate as our simulation data. So those are fed from our analog outputs here through to the ADCs of our PMU. This is one for voltage and one for current. The PMU normally has a D-dot plate for sensing voltage and a Hall effect sensor for sensing current, but which would be useful for a real grid, but we can't generate signals large enough for our PMU to sense. So the PMU will sense this phasor data and then transmit it to the Arduino using a serial port. Once our simulation data is sent to our signal generator, I can press this button, which will trigger it to output the data to the PMU, which will again then send the phasors to the Arduino, which will make a classification and send it to my computer, and it'll display them on a serial port right here. This signal generator right here, just putting out square waves at the exact frequency of our simulation data. This is used because the frequency stability of this signal generator is not that great. So this is necessary to make sure our waveforms are actually consistent in time and aren't jumping around. There's not too much jitter in our sample clock. So in order to make this data suitable for our PMU, we have to first scale it down. Right now we see about 500 volts roughly and tens of amps, which our PMU can't handle. So we have to scale that data down into the 0 to 3.3 volt range that our PMU is able to handle. This current is in voltage now because this is representing the signal seen by our ADC. So if I continue on, now the signal generator is awaiting this trigger. I can press this button here, and we see that the Arduino is predicted class 6, which is the same class that we were expecting it to predict. And keep going. So here's another. There's a class 5 now. Instead of turning on the 10 and 20 horsepower motor, just turning on the 20 horsepower motor. You can see it's a similar waveform where there's the distortion half cycle later and the increase in current. If we carry on, we can trigger this, and we see that's predicted class 5 as we expected. I'm just gonna run through a couple more simulations now. Here's another class 1, where we've now islanded the microgrid. So this is, say there was some instability on the main grid, you might want to disconnect your microgrid from the main grid so it's able to run by itself independently. So we want to know if that happens. So you can see here, there's no large current spikes, but you can see some distortion in the waveform. So if we carry on, looking for class 1 hopefully, and it predicts class 1 correctly. I'm going to continue to do a couple more tests. So here's just the 20 horsepower motor again, which we've already seen. We're looking for class 5 and run the test. Here's class 5 again. Just run a couple more. Here's class 5 again. I'll speed through this. So you've already seen this. Class 5 again. And here's class 2, where we add a 20 kilowatt load. So this is not an induction motor, so we don't see the same current spikes from inrush current, we just see a much cleaner wave, but our current is increasing. So let's see how we do on class 2. Carry on, waiting the trigger. I'll press the trigger, and I produced class 2 correctly. That's great. A couple more, and that'll be all the classes. So here's the class 5 again, which you've already seen. So continue, trigger that. And we should be coming up on a new class. Here's class 0. So this is no disruption. There's nothing happens, nothing of interest happens at 0.1 seconds. This makes up a very small portion of our data set, so it actually has difficulty classifying this in general. So we'll trigger our setup again, and we see it mispredicted class 3. So there still needs to be some work done for that class. So we need to add more data for that data set. If we run one more, here's class 1 again. In class 1, here's the prediction. I think a couple more tests, we should hit class 4, which we haven't seen yet. Here's island again, class 1, again the relatively undistorted waveform. Continue and trigger, that's correct again. And here is class 3. So this is where the photovoltaic cell, for example, has a cloud go over it, so now it's not generating as much as it was earlier. That generation from that renewable resource has dropped significantly. And we predict class 3 correctly. Should be the last one. Class 4, here's class 4, just adding the 10 horsepower motor. So you can see again there's a current increase, some spikes afterwards. And if we continue, go ahead and press the trigger. And we predict class 4 correctly. That's the demo, thank you.